Welcome to session 18 on plane stress. In today's sessions, we're going to have an opportunity to cover in-plane principal and max shear stresses. So our first portion will focus on what are in-plane principal stresses. Then the second portion will focus on what are in-plane max shear stresses. And we'll be able to calculate them using graphical methods and using the scripts. But the third part and the fourth part are going to focus on the actual calculations that make it very quick. So some of you may be tempted to just jump right to part 3 and part 4. I hope, though, that you'll take a minute to watch part 1 and part 2 so that you're able to get a little bit of an understanding of how the orientation of these rotational, or these not rotational, but these elements, these stress elements, relates to the in-plane principal shear stresses and max in-plane max shear stresses. Okay, so as a review, we do have a general set of equations for transformations in 2 dimensions, and I didn't include using the stress tensors this time, but we can actually do it in 3 dimensions as well, as we discussed in session 16. Going back, though, to what we covered in session 17 on, I'm sorry, it was actually the stress tensors were in session 17. We're in session 18. Okay, so what we've essentially established are a set of equations that allow us to go from one orientation that's generally given and in terms of sigma x, sigma y, tau xy, and then go to a rotation or a rotated element or transformed element that has sigma x prime, sigma y prime, and tau x y prime, or x prime y prime, better said usually. So now, if we have this angle of rotation, okay, given by theta, we can think about it as, okay, what is this face, which was kind of the x face and now is the x prime face, what has it experienced? We can think of it as, okay, what has this kind of negative y prime face over here experienced? Okay, and if we're careful, we can also think about it in terms of how a slice taken through the element would be related to the angle theta as well. Okay, so in the past assignment, we saw some examples where the theta was given in this corner, okay, this bottom right corner, okay, instead of in this top corner. And as we talked about last time, it's often a good idea to keep the triangles that we draw in these cases very exaggerated, okay? But yes, we can go from a slice, okay, and then think about this theta with respect to a vertical as being the same angle here. And to kind of depict that, you can extend this line out, see how this, if we call this face like the sigma x prime face, okay, opening to the right, then we see that we're able to draw, say, this same element and put this same angle that we had here as the angle that was in this corner right here. And this is review, okay? This is review from what we covered last time. Just thought that given some of the comments that that were in the chat or in the group me, that it would be good to maybe just emphasize this point for a second. And of course, we get our general set of equations for transformation from doing equilibrium on a triangular element or on a couple of triangular elements, actually, and then doing equilibrium, performing equilibrium on forces. Okay, so these stresses are acting over areas, as we've seen here. And we have this delta A cosine face, and delta A sine face. All right. So we have this general depiction. Maybe I could have called it the general set of depictions, okay, for rotating a element in plane stress. Okay, but here come the equations. All right, with an example that we did from last time. This was example 17.3. So if we want to figure out sigma x prime, we have this equation where it's equal to the average of the sigma x and sigma y plus the difference divided by 2 times cosine 2 theta plus tau xy sine 2 theta. And if we want to figure out the tau x prime y prime, and we can use this equation. And again, this comes from our use of equilibrium on the sliced stress element. And we can also have an expression for sigma y prime. And as we discussed last time, this is kind of like plugging theta plus 90 degrees into this equation up here. And then we get this one down here. Okay, so that's almost everything we're going to recover from session 17. We're going to just do a little bit more of review here. Okay, we also discussed how we can plot the output of these stress transformation equations, and you see these plots here, and we could identify where we might have mins or maxes, or identify what sigma x prime and what tau x prime y prime and what sigma y prime would be at a given angle of rotation. Okay, so now we've got that basis covered again. Let's talk about in-plane principal stresses. And so this is some jargon that we're going to introduce. It's more than jargon. It has technical meaning, right? But the first thing here is like, what are they talking about? Okay, and this is not principle like I'm very principled and in my views on whatever world politics. No, that's not what we're talking about. These are principles. So these are kind of like primary, okay, stresses, and they're normal stresses. And these are acting on what we call principal faces, and there are no shear stresses, only normal stresses acting on the element. Now, what do we mean? We start with a general element, and obviously there are shear stresses drawn here, right? They could be 0, but whatever. This is an arbitrary planar element, okay, in plane stress. And what we're saying is that we can find an orientation, okay, of rotation, and it's usually given by theta p, such that we only have normal stresses. So this is where we go, all right? So we have principal faces, we have principal stresses. So principal faces will be these faces at a given orientation. So they're just normal faces, right, that you have. And we would have had some sigma x potentially initially, right? And this, if there's a tau xy present here, that then means that this is not a principal phase. These are not principal phases. If tau xy is equal to 0, then yes, these sigma x and sigma y would be principal faces, because what we're saying is that we have normal stresses acting perpendicular to the principal faces, and there is no shear stress. Okay, so we find an orientation such that we can find a sigma 1 and a sigma 2 that are orthogonal to these faces, and there are no shear stresses. Okay, pretty straightforward concept, right? And we often call one sigma p1 and sigma p2. Now, these terms can get a little bit confusing. Okay, it's not super duper important that you have, hey, this is the P1, this is the P2, all right? But what is kind of typically followed as a rule, all right, and we might break that here a little bit. Actually, well, let's see, we'll be pretty consistent, I think, in these slides, is that sigma 1, okay, is typically larger than sigma 2, okay? So what you'll see is that people will write like a sigma 1, sigma 2, sigma 3, okay? And you can read Hibbler's book about this or look at other texts. And typically they're in descending order, okay? So it may not be that your theta P1 is associated with sigma. Well, we're probably going to associate theta P1 with the biggest one, but it may not be the closest angle of rotation, okay, shall we say, acting on this face. All right, so don't get too caught up in, okay, this one's P1, this one's P2. But what's important is that there is a state where you have, or a depiction or an orientation, right, of the state of stress that has zero shear stress. Yeah, you only have normal stresses. And you're like, why do we even care about this? Why do we care? We care because when we discuss criteria for failure, brittle materials typically fail due to normal stresses, okay? Those materials get more pulled apart, and it's important for us to be able to identify what these maximum normal stresses are. And now we're saying we can figure out what the maximum normal stresses are. With this transformation, the shear stresses go to zero, and now we have a maximum normal stress in one direction and another normal stress in another direction, okay? And when we get to criteria, we'll talk about different aspects of what to do with these normal stresses, all right? But this process allows us to identify maximum in-plane principal stresses, okay? That should also probably be something that we repeat a lot here, this word in-plane, okay? It turns out, and spoiler alert, when we get to our next session, you can have principal stresses that are actually larger than these in-plane principal stresses, okay? But will be or different, okay? Shall we say? Yeah, and so we'll cover those in the next session. Okay, so let's do an example. If we have an element that has sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equals 10 megapascals, what are the in-plane principal stresses, and what is the associated angle of rotation, theta p? All right, so we'll go back and think about what, kind of generally speaking, we're going to show how you calculate these quickly in the future, but now we're just trying to kind of explain what is happening and what the state of stress looks like. So we're trying to rotate to get max normal stresses and zero shear stress. Okay, so we're looking for something where we have zero shear stress, essentially. And we have what we consider to be kind of at least one maximum normal stress. Okay. And I suggest highly for this particular session, and the last session too, that you do look at the collab, you get it running, okay, because it will make solving the problems easier and hopefully also bring to light some of the actual underpinnings or the underlying workings of these stress transformation equations. Because I don't want you to plot every single one of these little points by hand, right? We can put an array of angles, and then it spits out what the corresponding sigma x primes are. We can put an array of angles, and we can get, spit out a corresponding set of sigma y primes. And of course, when the angle is equal to 0 degrees, right, that's the same thing as what sigma x was originally, and what sigma y was originally. Okay, but we have sigma x primes, sigma y primes, and not all, right, not that we're looking for very specific ones where we have zero shear stress when we're talking about in-plane principal stresses. And we essentially have only normal stresses. We got to find this orientation or these orientations. So let's take a look. When we max out, all right, on a stress, on a normal stress? Okay, well, it looks like we can max out here when the sigma x prime, all right, is about this value. Okay, what is sigma x prime? It's something, something a little bit greater than 75 degrees, right? Maybe it's, I don't know. We'll see. We'll actually get the exact number here. I think it's like 79 degrees or something. But anyway, it's right there. Okay, and we can call that sigma p1, and that's corresponding to a maximum normal stress. And it actually is corresponding to a minimum normal stress in sigma y prime. We have another one, all right, when we have a maximum, all right, in the sigma y prime right here, okay, and that corresponds to a minimum in the sigma x prime. And we might consider that to be sigma p2, okay? And now if we look at when is the shear stress equal to 0, okay, we can draw this nice little line that's going through 0, and we see that it's going through around here, okay? And, these things may not be aligned perfectly. They're just hand-drawn. And here's another one at sigma p2. And we're starting to say, hey, wait a second, this is looking kind of similar, right? And that's what it should be doing, okay? We see it, we have a theta p1, theta p2, all right, where we have a theta x prime at a max, a theta x prime at a minimum, where a theta y prime is at a max. And then we have two locations, two orientations where we have the shear stress being equal to a minimum, okay? So if we run the code, additional code, so you plot in the Colab, and then you go ahead and you run the next section in the Colab, all right, which you have available, what we can do is spit out, okay, a bunch of results, okay, for the maxima sigma x prime, maxima sigma, or minimum sigma x prime typo, okay, and we can identify these angles, right? So remember we were saying a second ago that looked like the maxima sigma x prime, if we go back, was happening around maybe 79 degrees, okay, right here. And that's also where the tau xy prime, x prime, y prime, okay, the shear stress was equal to 0. Okay, so that's what we calculated exactly, or pretty exactly numerically. Okay, you can take a look at the code. Essentially what we're doing is we're plotting 1,000 points and then looking at when is the sigma x prime a maximum, when is the sigma x prime a minimum, when is the and actually that's what we're doing here, and then we're plotting the associated shear stress. And then we can also do the same looking at when is sigma y prime a maximum, when is sigma y prime a minimum, and then plot the associated shear stress as well. Okay, and we see that shear stress is about equal to 0. Okay, this is numerical. Doesn't always spit out exactly 0. Okay, so you see that there's this negative here. Or, when you're doing numerical problems, as you've seen in the past, like when we did the rotations, you were getting things like 6 times 10 to the minus 17th or something like that, right? Those are essentially 0, okay, when you do these types of problems. So we get theta p is equal to 79.1 degrees, all right? Or one of them is at least, all right, for one of them. And this means that we have a sigma 1, all right, which we maybe draw in that direction, equal to sigma x prime, which was 102 megapascals. And a sigma 2, all right, that's equal to 48 megapascals. If we go to 169.1 degrees, what are we seeing? We see now that sigma 1, all right, is actually going to be, if we go with the max one, it's actually equal to the sigma y prime, which is 102 megapascals. And sigma 2, the lower one, is actually associated with sigma x prime, okay, the x prime direction, and that's equal to 48 megapascals, as you see here. Okay. Let's do another example. Very similar. In this case, we have sigma x equals 50 megapascals, sigma y equals 100 megapascals, right? And you're like, wait, they're a factor of 2 of each other. So this could be associated with something kind of special. And it is. This would be like the loading of a cylindrical pressure vessel, right? Where we have one of the sigmas equal to twice the other sigmas, PR over T versus PR over 2T. And what we're saying here is that the shear stress is equal to 0, right? That's also associated with a cylindrical pressure vessel because we have no shear stress on these planar elements on the surface of a pressure vessel, at least in this particular orientation, right? At least in this particular orientation. So the question is, what are the in-plane principal stresses and what is the associated angle of rotation theta p? So once again, we can use the collab, which is included, and we can look at the outputs, which are these graphs here. And if we draw a line going through the maximum sigma x prime, which actually also goes through the minimum sigma y prime, okay, and we look at where the maximum y prime is, sigma y prime is, okay, it's at 0. So, it's kind of a silly question because what we're saying is, hey, tell us what you have to do to rotate to get in plane principal stresses. And if you have no shear stress, right, like we're showing here with this particular orientation, you don't, or we don't have to do any rotation. Okay, so if we just stay at 0, we're fine. Okay, so 0, 0. Okay. And so this is, is which one's theta P1, which one's theta P2? You can kind of guess. I kind of said, okay, well, this time I'm going to say theta P1 is associated with when sigma x prime is a max. All right, that means I have to rotate 90 degrees, right? Because in this case, sigma y was larger than sigma x. So we had to rotate 90 degrees to make the sigma x line up with the sigma y. Okay, so if we, again, look at this element and we say there are no shear stresses in the original orientation, that means that the output, when you run the code, is quite boring. Okay, so what's the maximum sigma x prime? Well, it becomes sigma y, okay, right, when we rotate by that's, wait, hold on. Yeah, so yes, this is, okay, so we're doing this one essentially. So if we rotate by 90 degrees, right, then sigma 1, okay, is going to be the sigma x prime in this direction, right? That was the sigma y, the original one, and so that's 100 megapascals. If we stayed right where we were, right, then the maximum is sigma y prime. All right, there's no rotation. Sigma y prime is equal to sigma y when you have 0 degree rotation. And so that's 100 megapascals, okay, as you see here and here. Okay, so this example is just to demonstrate that, yes, if you're given an element that has no shear stress from the beginning, you don't have to really rotate. But you could still rotate 90 degrees if you want to flip your x's and y's, okay? Question 18.1 for you all, okay, is given an element of sigma x equals 50 megapascals, sigma y equals minus 10 megapascals, and tau xy equals 10 megapascals. What are in-plane principal stresses, and what are the associated angles of rotation, theta p? Okay, and in this case, the way this one is set up, you're only going to need to put in one theta p, okay? And but you are going to be looking for a couple of in-plane principal stresses, okay? And you can go to Canvas and do this problem and solve it out. All right. So this concludes our first portion, all right, on in-plane principal and max shear stresses. See you in the next session.